Today we're digging into reinforcement learning, RL, basically. Forget programming every step. Think teaching an AI through, well, experience. Good moves get rewarded, bad ones, not so much. We're aiming to really boil down the core ideas using a key text as our guide, uncovering what makes these learning agents tick.
Exactly. We're going right to the foundations. How does an agent sense its world, choose an action, and chase a goal that's defined purely by rewards? It's, on the surface, a simple loop, but it allows for incredibly complex stuff to emerge.
Yeah, and the history is pretty cool, too. It's like two streams merging, right?
Yeah.
You had psychologists looking at animal learning, do good thing, get treat, repeat. And then separately, mathematicians working on optimal control, dynamic programming, finding the best sequence of decisions.
Precisely. And these seemingly separate fields kind of came together to form modern RL. And what's great is seeing these abstract ideas play out. Like, think of a baby gazelle learning to run.
Right, no instruction manual there.
Yeah. No, it's pure trial and error, figuring out muscle coordination. That's RL. Or a robot deciding, task versus charging station.
Balancing immediate goals with staying powered up.
Exactly. And it's
Yeah.
always weighing the reward task done versus battery full. Even, like you said, making breakfast.
Yeah.
Mm.
Opening the cupboard, pouring cereal. Each step gets you closer to the reward. Food.
Mm.
And we should mention, there are different ways these agents learn. Some build a sort of internal map to plan ahead.
Those are the model-based ones.
Right. And others just learn straight from doing stuff. Model free. We'll get into both.
Mm.
Okay, so let's dive into the actual building blocks. What are the core pieces?
Okay, so the absolute core is this loop, agent, environment. The agent sees the environment's state.
Like where it is, what's around it.
Yep. Then it picks an action. And based on that action, it gets a reward, maybe positive, maybe negative, and lands in a next state. State, action, reward, next state. That's the cycle over and over.
And the whole point is the goal, right?
Yeah.
Which in RL terms means maximizing the total reward over time, the reward hypothesis.
Exactly. It's not just about the next immediate reward, but the cumulative reward, the long game, strategic thinking, essentially.
Makes sense. And there's a difference between tasks that end, like a game, and ones that just keep going.
Right. We call them episodic tasks, like a game of chess, definite end, and continuing tasks, like maybe that robot navigating forever. In both, the goal is to maximize the return. That's the sum of future rewards, often discounted so that sooner rewards count a bit more.
Discounted. Okay. Now, you mentioned something crucial, the Markov property. What's that about? Why is it important?
Yes. The Markov property is a simplifying assumption, basically. It says the future only depends on the current state, not the whole history of how you got there.
So what matters is where I am now, not the specific path I took.
Precisely. Think of chess again. The best move depends on the current board, not how the pieces got into that exact configuration 5 moves ago. It makes the learning problem much, much more manageable. The agent doesn't need this massive memory of everything, just the current snapshot.
Okay, that helps. So the agent's in a state, it knows the Markov property applies. How does it actually decide what to do? That's policies and value functions.
Exactly. The policy is the agent's strategy. It maps states to actions. It could be deterministic in this state, always do this, or probabilistic in this state, maybe do action A 70% of the time, action B 30%.
So the policy is the how to act rulebook.
Pretty much. And value functions help it figure out how good it is to be in a certain state or to take a certain action in a state. The state value function estimates the expected total future reward starting from that state. The action value function estimates the reward from taking a specific action in that state and then following the policy thereafter.
So values guide the policy improvement. High value states or actions are desirable.
Right. They provide the feedback loop for learning a better policy. You want to find the policy that leads to the highest value states.
Okay, so it's learning which moves are good in the long run. But what if it doesn't know? What if there's an action it's never tried? This sounds like that exploration versus exploitation thing.
You got it. That's a fundamental tension in RL. Should the agent exploit its current knowledge, pick the action it thinks is best based on past experience? Or should it explore? Try something new, maybe less certain. That could potentially be much better. It's a constant balancing act.
And the classic example is the N-armed bandit problem. Sounds a bit like Vegas.
Yeah, it's a simplified version. Imagine you have several slot machines, or bandits. Each pays out differently, but you don't know how. You have limited pulls. Do you keep pulling the lever on the one that's paid out okay so far, exploitation? Or try the others to gather more info, hoping for a bigger jackpot later exploration.
Right. Immediate gain versus potentially greater future gain. How do RL agents actually handle this?
There are a few common strategies. One popular one is A greedy, pronounced epsilon greedy.
Epsilon greedy, okay.
Most of the time, say 1%, the agent picks the action with the highest estimated value, the greedy action, exploitation. But a small fraction of the time, R%, it just picks a random action. That's the exploration bit.
So mostly greedy, but sometimes takes a random punt just to see what happens.
Exactly. Another way is upper confidence bound, or UCB. This one is a bit smarter. It considers not just how good an action seems, its estimated value, but also how uncertain that estimate is. Actions it hasn't tried much have higher uncertainty.
Ah, so it might try an action that looks slightly worse if it's really unsure about it, because it could be amazing.
Precisely. It adds a bonus for uncertainty, encouraging exploration of less-known options. There are other tricks too, like optimistic initial values, assuming all actions are great, initially forces exploration early on. And gradient bandit algorithms use a different mathematical approach based on preferences.
So lots of ways to tackle it.
Yeah.
But the core challenge remains finding that sweet spot between using what you know and trying new things.
And this connects to something called associative search, or contextual bandits. It's like the bandit problem, but the best action depends on the current situation or context, a step closer to full RL.
Okay, got it. So the agent is exploiting. How does it actually learn the values of actions? How does it update its estimates?
Right, learning methods. A key idea is estimating those action values. We mentioned the Q values.
Yeah.
Q for quality, maybe. These Q values estimate the return from taking action A in state PES. If you have good Q values, the best policy is often just to pick the action with the highest Q value in your current state.
And these Q values get updated as the agent experiences things incrementally.
Yes, incrementally. It doesn't wait for the whole game or task to end, necessarily. The general idea for updates is often new estimate, old estimate, plus step size. Target, old estimate.
Okay, so you adjust the old estimate based on some target value scaled by a learning rate or step size.
Exactly. And what that target is makes the difference between methods like Monte Carlo and temporal difference learning.
Ah, okay. Monte Carlo versus PD, what's the difference there?
So, Monte Carlo, or MC, methods learn from complete episodes. You run through the whole task from start to finish. Then you look at the actual total reward, the return you got from each state you visited, and average those returns to update your value estimate for that state.
So MC waits till the end and uses the real final outcome.
Right. Temporal difference, or TD, learning is different. It learns on each step. It doesn't wait for the end. After taking an action, getting a reward, and landing in the next state, it immediately updates the value of the previous state. And crucially, it used the estimated value of the next state as part of its update target. This is called bootstrapping, updating an estimate based partly on another estimate.
Bootstrapping. Okay, so TD uses the immediate reward plus its current guess about the future.
Precisely. The difference between its prediction before the step and this new target, immediate reward plus discounted value of next state, is the TD error. It learns by trying to reduce this error.
So TD learns faster, potentially, because it updates constantly, but it's using estimates, while MC uses actual final returns.
That's a good way to put it. TD can learn online, step by step. MC has to wait. And Q learning. That's a very common TD method, isn't it?
Yes, Q learning is a specific and very important TD algorithm. It's off policy.
Off policy, meaning?
It means it learns the optimal Q values directly, even if the actions it's actually taking to explore are sometimes random or suboptimal. It learns about the greedy policy while behaving, possibly non-greedily. We could also briefly mention afterstates. Sometimes, especially in games like chess or Go, the immediate result of an action, the board position after the move, is known deterministically.
Ah, okay. You know exactly what the board will look like.
Right, so you can estimate the value of that after state directly, which
Okay.
can sometimes be more efficient than estimating the value of the state-action pair.
Interesting detail. Okay, so far we've mostly talked about learning directly from experience, model-free. What about building that internal map we mentioned, planning with models?
Right, so a model of the environment is something the agent learns or is given. It predicts, given a state and an action, what the next state and reward will be. Like a simulator in its head.
Kind of, yeah. Planning is using this model to think ahead, to consider possible future situations without actually having to experience them in the real world. You can simulate taking an action, see the predicted next state and reward from the model, and use that simulated experience to update your values or policy.
So model-based methods use this internal simulation. Model-free methods just react to real experience.
Broadly, yes. Planning lets the agent try out sequences of actions internally. DynaQ is a classic architecture that blends both. DynaQ learns directly from real steps, like Q-learning, but it also learns a model of the environment. Then it uses this learned model to generate lots of simulated experiences and learns from those too, usually in between real steps.
Wow, okay, so it gets more learning bang for its buck from each real interaction by supplementing it with mental rehearsals.
That's the idea. It can often learn much faster, especially if real-world interaction is slow or expensive,
Okay.
but there's a catch. What if the model is wrong? If your internal simulator doesn't match reality, the plans you make based on it might be bad.
Ah, garbage in, garbage out.
Pretty much.
Right.
So even with a model, you still need exploration. You need to take action sometimes just to test if your model is accurate and improve it. And when we talk about using the model, we might do full backups considering all possible next states the model predicts, or sample backups just simulating one possible outcome. Full backups are more thorough but computationally heavier.
Okay, that makes sense. Now, a big challenge we haven't really addressed, what if the world is huge? Like millions or billions of states. You can't have a lookup table for Q values then.
Exactly. That's where function approximation comes in. It's absolutely crucial for real-world scale problems. Instead of storing a separate value for every single state or every state action pair, we use a function like a neural network or maybe simpler linear functions, decision trees that takes the state, and maybe action as input and outputs an estimated value.
So it learns a general pattern instead of memorizing individual values.
Precisely. The function has parameters think weights in a neural network. We adjust these parameters based on experience, typically using gradient descent methods. The goal is still to minimize the error, like the TD error, but now we're adjusting the function's parameters to make its output closer to the target value.
And the benefit is generalization. Learning about one state helps you estimate values for similar, unseen states.
That's the key advantage. An update based on experience in one state automatically influences the estimated values of many other states because they share the same function parameters. We talked about TD learning. There's a variant called TD using eligibility traces. This is particularly useful with function approximation.
Eligibility traces, what do they do?
They're a mechanism for credit assignment. When you get a reward or a TD error, an eligibility trace helps distribute that feedback back to the preceding states and actions that were likely responsible for reaching the current situation. It bridges the gap between immediate TD updates and waiting for the end, like MC.
So it helps figure out which earlier moves were important for the eventual outcome.
In essence, yes, especially over longer sequences. And common ways to use function approximation involve representing the state using a set of features. Linear function approximation, where the value is just a weighted sum of these features, is a foundational technique. Things like tile coding or coarse coding are clever ways to create these features from raw state information, allowing different levels of generalization.
Tile coding. Sounds like dividing up the state space.
Sort of, yeah. It overlays multiple grids onto the state space, and the active tiles form the features. It allows for generalization but also some specificity. And these ideas combine into algorithms like gradient descent SARSA or Watkins Q, which apply these control methods using function approximation and eligibility traces.
Wow, okay, so we go from simple tables to these powerful function approximators to handle really complex environments. It's amazing how these concepts have led to actual breakthroughs. Can you share some famous examples?
Oh, absolutely. One of the most celebrated is TD Gammon. This was back in the 90s. It was a backgammon program that learned to play at a world-class level purely through self-play, just playing millions of games against itself.
No human strategies programmed in?
Nope. It used TD learning, specifically TD, with a neural network as the function approximator to evaluate board positions. It discovered strategies that surprised human experts.
Incredible. Just learning from the reward of winning or losing. What else?
Well, much earlier, there was Arthur Samuel's checkers player in the 50s and 60s. It used techniques that we now recognize as related to RL, including a form of learning value functions and generalization. It was really ahead of its time.
Foreshadowing modern methods. Any non-game examples?
Sure. In robotics, there's the acrobat swing-up task. It's
Right.
a classic control problem, a tooling pendulum, only the joint is actuated, not the tip. The goal is to swing the tip up above a certain height. It's tricky because it's underactuated and requires complex nonlinear control. Algorithms like SARSA with function approximation, like tile coding, were shown to solve this effectively.
So learning complex physical maneuvers.
Exactly. Other areas include things like elevator dispatching, optimizing which elevator goes where to minimize waiting times for everyone in a building. That's a large-scale sequential decision problem. Also, dynamic channel allocation in cellular networks, assigning radio channels to calls efficiently to maximize network capacity and minimize interference. RL has been applied there too.
Real-world optimization problems.
Yep. And even things like job shop scheduling, figuring out the best order to process jobs on different machines in a factory, that's a tough combinatorial optimization problem where TD with neural networks has shown promise.
It's really impressive, the sheer breadth. Games, robotics, logistics, telecoms.
Yeah.
It shows how versatile this core idea of learning from rewards actually is. Okay, so as we wrap up this deep dive, let's just quickly pull together the main threads we've followed.
Sounds good. We started with the basics: the agent, the environment, the state action reward loop, the whole goal being maximizing cumulative reward. We hit the crucial exploration versus exploitation dilemma, the need to try new things versus sticking with known good ones.
Right, with methods like epsilon greedy and UCB.
Then we looked at how agents learn values Monte Carlo learning from whole episodes, and temporal difference, or TD learning, updating step by step, bootstrapping off its own estimates, like in Q learning.
And the idea of using models for planning, like in DynaQ, to speed things up, but also the risk of model errors.
Exactly. And finally, the necessity of function approximation using neural nets or other functions when state spaces get too big, allowing generalization, often combined with eligibility traces like TD.
And those examples, from TD Gammon to robotics and scheduling, really drive home how powerful these techniques can be in practice. So here's a final thought for you to chew on. Given how RL can learn such complex stuff in so many areas, where do you think we might see it pop up next? What are some maybe unexpected domains where reinforcement learning could make a really significant impact down the line?
That's a great question to ponder. The potential feels vast.
It really does. It's a field that's constantly evolving. We definitely encourage you to keep exploring it and the foundational ideas we touched on today. Thanks for joining us on the Deep Dive.